Hi, this is Curtis Brown. I'm here with Robert Ahdoot, and I'm super excited to welcome you to the video 2 in our Smart Space videos. This time we're going to be talking a lot about slope. And so, Robert, I'll let you go ahead and take it away from here.
Okay, so thanks, Kurt. So yeah, last time we were talking about, in open, vulnerable fashion, the number of hours I spend glued and melting into becoming one with my smartphone screen like this
Right.
per day, right? We have 24 hours in a day to live, eat, sleep, and do all the things between. And it turns out that data showed that I spent an average of 3 hours a day on my phone, 3 hours.
All right.
So what we can do is we can depict that in a chart and then see how that comes out visually in a graph. So it's great. You have the first column marked as days, and then we can
I've got a
start
column here for days and one for hours. So
rocking. So let's see, one day would be 3 hours.
One day would be, okay.
3 hours, there it is. Boom, and it shows up so nicely right there on the table there. Right, 2 days, 6 hours, right? Every day we add an additional 3 hours.
I heard you say 3, so I just thought I'd type that in.
Right, I was like, yeah, maybe did I drop my phone in the sewer? 5.
Let's go to 5 days. 5 days,
Yeah,
okay?
5 days is good. Yeah,
All right.
5 days is good. That's good. Yeah, that's good. I love how you have like control over the axes. And so, could you possibly change hours to phone hours? Is that an easy
Oh,
fix?
sure. We can rename that. Yeah.
Rocking.
That
That's
phone
like the
hours.
Y axis. Rocking. So then it just shows up
Hours.
nicely there. Phone hours. Beautiful.
Very good.
Yeah, so then we could see like that number of days compared to the number of hours on the phone, right? A reminder that this is kind of a high level comparison because technically it's comparing time to time, but we know that one value of time is constantly marching on, which is that x-axis, and the other axis is the thing that we supposedly have control over, we should have control over, which is the hours on the phone. I love that you're trying to show it in different ways. It's good. You have control over it. While we look at this line, it begs the question what the slope of that line is. Slope, aka is steepness, the steepness of the line. You know, immediately when we think of slope, we might think of something like skiing or even something like roads, what the slope of a road is. You know, you could say like this automatically feels like more steepness or more slope. Whereas if I went a little more shallow, we would say that this is a lesser slope, maybe, if people are trying to get like familiar and acclimated with this concept of slope. Steeper slope, which is like a higher number, maybe. If you had to guess, this would be a higher slope. This would be somewhat of a lower slope.
Okay.
In fact, in something like this, a skiing metaphor works really well. You don't have to know anything about slope, but if you were standing right here, I'm not a skier, by the way. I never have been. I always fall down.
Oh, you're missing out, man.
I'm missing out on no back pain. Okay, so thanks. I'm not gonna do that anymore. I'm not gonna like get ahead of the pain with all these back relaxers. Just meet me in the ocean. So if you're skiing here, are you going anywhere? Are you moving anywhere? Is gravity taking you anywhere? Answer is clearly no. You would just be stagnant, and so that's like a zero slope. So it would be really helpful for us to actually pin or create a numerical value for the steepness or the slope of the line that you just created.
Yeah.
All right. And I'm gonna show you how we could do that with a very personal example. All right. So I'm gonna share my screen.
All right. Let me know when you're ready.
All right. Did it.
Okay, you're ready?
All right. Yeah. All right. So here we are. So this is a reminder. This is 3 hours a day on the phone. And I want to introduce you to a sign that I saw. I'm glad you brought up I'm missing out, and that for some reason I went to the beach. So for several years I lived in Malibu, and on the way down to Malibu are these beautiful canyon roads from the city of LA down into the canyon, and then drops you off right onto Pacific Coast Highway. At the end of that tunnel, at the last bit of the road there, about 5 miles, is a very steep road.
Right.
And there's a sign that says here, this like 8% grade or 8% steepness. And it's interesting. I don't think many people really truly understand what this means. It definitely looks like it's steep, and trucks beware for the braking, you know, there's even a lane for runaway trucks. I'm telling you, right in front of my old apartment, there was a loose gravel and big barrels of water in case trucks lost their brakes going down this big road. So it's a big deal to understand this concept of steepness. And I saw this sign every day going to and from school. So we could talk about what it means. So 8%, literally percent, in case people don't know, per means out of, cent like a century, or cents of a dollar is 100.
Yeah.
So 8%.
Cent is 100. Mm-hmm.
Yeah, cent is 100. Per means out of. So if you're saying 8%, that's the fraction 8 over 100. And the slope here is 8 over 100. So we could just pick our units, let's say feet, for example.
Yeah, feet works.
Feet works. All right. So what this means in terms of steepness, the way steepness is measured is how far up and down we're going, up to down ratio, up or down, compared to how far right or left. So let's actually depict this.
Or left.
It's a vertical space compared to a horizontal space. The fancy term for this in the schools, and it's always fun, give it a little thickness too. Rise over run, it's always fun. 2 R's. Rise over run. Rise means up and down. Run means horizontal.
Sure. That's a nice visual, nice way for me to think about it. You know, I can connect this to like vertical. I don't really rise horizontal. I don't know too many people that can run straight up. You know.
Spider-Man. Yeah, run up the wall. And a fun thing
Spider-Man,
I like to say, Spider-Man, that's it, going up. A fun thing I like to say also is that the rise is equivalent to the y's in terms of y and x.
Nice.
Right? The rise is the wise, and you will be wise. Oh, puns!
Oh my goodness. Oh my goodness. Here it comes. Here it comes.
So the rise is the wise. Rise.
Nice.
Those statements are sticky. Beware. You might be saying that later this afternoon. Okay.
It could be.
So let's check it out. Let's compare 8 feet uppy downy to 100 feet lefty righty. All right. So we could pick a different color, maybe like a grayness of a road. And so this truck is contending with 8 feet of vertical space covered compared to 100. This is not to scale. It's not to scale. It would be, the 100 would be a lot longer if I was going to draw it to scale. It's like really fascinating to think of that on this road. See if I can go for glory here. There's my line, and then I can make it thicker. Yep. Boom. Boom. All right, I'm satisfied. So there we are. Okay, so there's the line. I created the line, and this is the road. So as the cars or trucks are going down this particular road, what they're doing is, as they traverse, they're covering 8 feet of horizontal space for every 100. Oh, excuse me. Good job. Thank you. Thank you. Teachers are human. 8 feet. Good catch. 8 feet of vertical space compared to 100 feet of horizontal space. And that's really fascinating because 8 feet in the land of a car is really, really a lot. 8 feet for a car, it's like almost getting as high as a basketball hoop. That's pretty high.
That's pretty much the height of your car. I mean, it's, most cars are maybe 6 feet, 7 feet, but a good sized pickup might be 8 feet off the ground. I mean,
if you could picture
Texas,
that,
we certainly have some of those, right?
Yes, yes. We call those Texas Instruments. Yeah. So they're an instrument of your joy. So now, but 100 feet horizontally is not a lot. So
No.
you could imagine though that 8 compared to 100, 8 is enough to warrant a sign from the
Mhm.
highway service to just be careful and not go so hard on the hill, not go so fast. So that's the slope. It's 8 to 100. Technically speaking, if we wanted to simplify, we would say, well, both of these 8 and 100 are divisible by 4.
Sure.
So we divide both by 4, and that slope technically breaks down. Divide by 4 is 2. Divide by 4 is 25. So we're going 2 feet vertically for every 25 horizontal, right? So this will be the last thing I do, and then I'd love to apply this up and downness to left and rightness on the graph that you created earlier. So if I go down 2, and then over 25, 2, 25. This is the concept. You could do this iteratively over and over, 2 to 25. And then I do it 3 times, 2 to 25. And then I did it the 4th time. And then I'm down at the bottom of the hill with brakes intact and no seatbelts deployed. There you go. So that's a breakdown on slope, rise over run. Okay, so can we apply those same up and down versus left and right to the graph that you made?
I think we can. I think
I'll
we wanted to have, so I'm ready to share my screen. So
all right, good.
We wanted to have or talk about that relationship between days and phone hours, right? And talk about the slope that's happening here, right? So walk me through kind of what you're thinking, because I think we maybe add a line to this. Can we equate these days and phone hours? Like, can we actually make an equation that says something like that?
We can. What we're going to do is let's not equate them right now. Let's actually just obtain the steepness or the slope of this line.
Oh, sure.
And then we'll see how that equates to the equation.
So what I see here, if I start at the first one and I look here at this next one, I have to move. Let's see, I'm looking at this. I've got my value is at 3 here, right?
Yeah, the vertical value, y.
I've got my vertical value. I've got this 0.13, right?
Yeah.
1 day, 3 hours.
Yeah.
And this next point that I have highlighted is at 2 days, 6 hours, right? So the distance between here and here, well, that's 3 and that's 6. Distance between them should be 3, right?
Right. So we just ask ourselves, if you wanted to get there, if you're playing a little like a 2D computer game, a little hop, 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 right?
Mm-hmm.
So start down at 1-3 again.
Okay.
So the question is, should we thinking about right or left first or up or down first?
It seems like we're talking about the number of phone hours per day, right? So to me, I might like to talk about moving to the right first, because truthfully, independence time is going to march on whether I wanted to or not, right? So
so this is fine. I look like a little bunny. So no, I don't want to go right first though. I know what you're saying though, and just in terms of, I want to be able to equip everyone watching so that for them to calculate the slope simply by looking at points, like you were doing right before. So if I wanted to gather the slope, I have to think of the rise first, right? And then we'll go over. We'll go over. So how far up was that? Like
so that looks to me like it was up 3.
Up 3, and then how far to the right?
1 unit, 1 day.
Right.
Mm-hmm.
So up 3 over 1. So
up
that's
3 hours.
Right. So that's 3 divided by 1. Right on.
Right.
So
3 divided by 1. Let's see if it's still the same. So if I'm here on day 2, and I want to get to day 3.
Yeah.
Does it remain the same? So
it does.
2, which is 6. And if I navigate over here to day 3, which is at 9 hours. So I rise 3, right? 6 to 9.
Yeah.
And then 1 day to the right.
Yeah.
So still 3 to 1.
what's fun is try go from 3.9. Let's go from 3.9 back to 1.3.
Okay.
It'll be the same.
So let's go. Are you saying that I do down 6?
Yeah, so now if we're asking rise first, we only ask ourselves if we're going up or down. So the answer is down, right? So we go down 6 units, which you just said. And then, so that's -6, -6 down. And then we're going right or left from here.
So I'm going to go left.
Left, and now left 2.
Left
so
2 units.
Left 2 is negative. Left is negative. So that was -6 over -2. -6 divided by -2 inevitably is
still 3.
3 again, right?
Still
so
positive 3.
It's fun. It's fun for me. It's like, it's encouraging to me to know no matter how we looked at this line, the slope is 3. That's it. The slope is, so we just discovered the slope of the line.
For sure.
Now to your question.
Yeah, question about can we equate these?
Right. Is it safe to say that y equals x?
Well,
does the phone hours?
Let's just put a function on there. Let's just put an equation.
Sure.
We're gonna say y equals x.
So y meaning phone hours. Our phone hours the same as days?
Yeah.
Like are they
our phone hours the same as days? So if we just plop that guy on there.
So this would be, all of them are the same. It's like 1 1 2 2 3 3 4 4. Yeah, I'm looking at 4 4 lines up nicely.
Yeah, it really does.
So
and another one at 8 8 8.
8 8. They're not the same. So I mean, they are the same, but ours is more. So what I want to do is I want to ask people to look at your table now, even look at the table, and what would we have to do to x, basically? What would we have to do? Can I grab the screen to conclude us off? Okay, I'll grab the screen. There we go. 1 2 3 go. So we had, let's do it. So if you have x, y, 1 3 2 6, that's all you need. So we have y equals x. No, clearly not. But what you can do is you could say y equals something x. Something. This can be something such that they are the same. And Kurt, we've seen this number before.
I think we've seen it.
Seen this number before. Anyone watching, you might know it already. What would I have to put here in front of x so that y is the same as it? What would I have to put in front of x to make y the same as it? The tension is building and growing.
I would say that we're probably multiplying by 3.
Bravo. And what's fun is, go ahead and take this back real quick.
Yeah,
the slope has been looking at us all along. The slope is embedded. The slope is embedded, hiding inside the equation. So I take it back here, stop. Okay.
All right. So what if we took this and changed our equation just a little bit? Instead of y equals x, what if we dropped that in and said, okay, now we have this equation that is y equals 3x. Y equals 3x. Or in our case, we have phone hours is equal to 3 times days.
Right.
We have phone hours is equal to 3 times days. That's what we really truly have here.
Right.
So we just was hidden right there in that equation.
Yeah, the slope is part of the way to create the equation of the line is using that slope itself hiding right inside. Yeah. So
totally,
that was cool.
Awesome.
Yeah.
Well, this was a cool introduction to slope. The idea of rate of change and slope, that was really a good context for us to be talking about. I really enjoyed this, Robert. So thank you for that. We'll conclude this video right here. So thank you, and we'll see you next time.
Bye. This is my slope. Goodbye.
Oh, nice. I like that.